Hello, everyone. Thanks for joining this workshop, part of the ML Ops Bay Area Micro Summit. If you do have any questions for Jules, you can ask them in the chat, just on the right-hand side. On a side note, workshop number 2 is going to be hosted at noon, and the talks will begin at 5:30. We're also going to be hosting community mic session at 5:05. So feel free to join the mic session, and then to hand over the mic to Jules for the workshop.
All right, thank you. Let me see if I can share my screen over here, application window, make sure that you all can see it. And let me start. How about now? Can you guys see everything?
Yes, we can see it, yeah.
Okay, well, thanks a lot. Well, good afternoon, good morning, rather, good afternoon, good evening, whatever time zone you are in. Welcome to the Toronto Machine Learning Series. I want to thank my host, Faraz, for inviting me for the second time. So I must have done something right the first time. But thanks a lot, Faraz, and congratulations on launching the Silicon Valley chapter of this. Now, I can't see you guys, and I can't look at the chat window because I'm in application mode. So I'll try to answer any question that I actually might have towards the end of this particular module. Normally, this is a 4 to 6 hour session. I'll try to squeeze everything in a little over an hour. So we'll try to go through this very fast. Again, my name is Jules Damji. I'm the developer advocate here at Databricks. Been here for a little 5 years, and I've had the good fortune to learn all the different things that Databricks has actually taught me. So today we're going to go through the introduction to MLflow, which is how you actually use MLflow to manage your entire life end-to-end cycle. And I've divided this particular presentation or workshop in 4 different modules because each module is a separate entity of its own and it serves a particular purpose. And so we're going to start first with the tracking module. But today, in this particular module, I'm sort of talk about what are the overall challenges that people like you who are developers out there who actually faces machine learning. You know, what are the concepts that motivated us to come up with this particular platform? And in particular, we'll go into the MLflow tracking as a first module. We'll see how we can use these tracking APIs to take your existing a machine learning model that you have, infuse the tracking API so you can actually track the parameters in experiments and runs and compare and contrast. And we'll do that using the Databricks Community Edition. Hopefully, most of you have registered it by now. And then we'll explore the UI to see how you can actually navigate through your experiments and run to compare and contrast some of the metrics that you're more interested in. And then we'll go through a quick hands-on tutorial for tracking. Now, there is a GitHub URL that I have all the workshop material in there, including the notebooks, including introduction, how to get started with community editions. Hopefully you had this sent to you. If not, I'm going to keep it here for 5 seconds. If you're interested to follow with the slides, I have the slides in each of the folder called slides directory. It's a PDF file, so you can actually bring up in your browser and look at that. So let's start with module 1 tracking. But before we get into tracking, I want to make an assertion, and most of you probably might be able to agree and relate with that, is that machine learning development is complex. The complexity does not stem from the fact that the math behind it is complex, although arguably, you know, there are aspects of it which require you to understand some statistical models and some theory behind it. It's not that the algorithms and the classes and the machine learning libraries that you're actually using are complex, although they've done a fairly good job of abstracting that a little bit and giving you the essential classes where you can actually use it with default parameters to get a fairly good, decent first run to build your particular model. The complexity stems from the methodology in which how you actually build a particular model from the inception to the production and how you approach software development cycle, which is quite different from, say, if you're coming from a traditional software development environment, which most of us who are making transition into ML will realize that there is a difference in the paradigm and how you actually go about doing it. And so if you compare those two, the way you do traditional software, which is machine learning, is that the goals are very different. Normally in a machine learning context, you are more interested in optimizing a particular metric. You want to make sure that you get accurate accuracy, so you feel confident that you can actually somehow deploy that particular model. Whereas if you look at the traditional traditional software, the goal is different. It's more functional. You're given a particular spec and you implement that. The quality of code depends on data in machine learning, because data actually makes a difference. Especially now, we're dealing with a massive amount of data where scale actually matter. Normally, in a traditional environment, you'll actually have only one stack or a couple of entities in the stack, where you'll have fewer libraries and fewer tools to work with. Whereas in ML stack, the stack is actually different. It needs to be of all the common machine learning libraries that you actually want to use, the different languages that you're going to use, and because of the fact that there's a proliferation of the open source. The open source sources, you will have a large stack of machine learning the libraries actually want, and the environments are actually quite different in which you actually want to deploy those. Excuse me, I'm going to drink some water. So this somehow is a very iterative process, because you have a data, you actually want to iterate over the experiments, and you want to make sure that the goal and the metric that you actually want to achieve comes from iterating that. So how do you actually do that? Now, if you look at your traditional ML application, this is the proverbial sort of life cycle that you actually deal with, and the different stages within that. And each stage you have different set of tools you actually want to use, and there are tuning parameters that you want to capture, and there are different configurations you want to capture. So what do you do when you actually have to tune? For example, you might be using pandas and Python to do some ETL to prepare your data, feature engineering, and there might be some tuning parameters you actually want to use. So you want to capture that particular tuning parameters. More particularly in training, when you're training the particular model, that's where the tuning parameters come in. You might be using a lot of hyperparameter tuning that you actually iterate over the model. So you want to capture that particular thing. So tuning is actually important as part of it. The second problem is that scale. You have to deal with this particular scale, because the fact that now we're actually dealing with large amounts of data, and we have to be able to deal that with actually the scale. So that's the third problem that you actually have to deal with to make sure that your machine learning cycle is scalable. The third problem is that how do you ensure that the model that you actually created in your development environment, when the data engineer, when the ML engineer actually created a particular model and handed it over as a model exchange to the application developer who's going to use that, is the same one that you actually used. So how do you make sure that the model exchange is identical? How do you reproduce those? How do you actually hand off with such confidence that what you develop is what you're going to deploy? So that's sort of the third order of problem. And then finally, we are living in a very data-centric society today. We are making a lot of data-driven decisions, and we have to be able to somehow governance and provenance come into play. We want to be able to query how the model was developed. We want to ask who actually used the particular model, when it was used, what were the stages it actually went through. So the provenance and governance actually come into play. And so these are all the different sort of complexities you got to deal with. So the question you might ask, Jules, is that, if this is so much a problem, how do the big companies who have actually built these particular platforms have resolved that? It turns out that some of these big companies that you actually hear about, who actually deploy models on an hourly basis, and a weekly basis, a monthly basis, have somehow standardized some of the early phases of training and experimenting and all that. But the problem is that, is it the platform quite open? In other words, if you left, for example, one company to go to the other one, can you actually take the transfer of knowledge and use the same languages that you actually want to, or use the same APIs, or do they actually support the overall open source platform? And we wanted to make sure that when we actually developed this particular platform, we used all the best things that all the different companies actually used in initial stages, but do it in an open manner so that we can actually allow developers can use the libraries they actually want to use, the diverse environments in which they want to deploy, and use that not only on the laptop, but also do that at scale on a larger organization. And so we thought, what can we actually do such that we build this on the principle of openness and the principle of first principle, where we provide them a set of APIs and we make it modular, right? Each of these particular different modules somehow address some of the problems that I talked about in this overall life cycle, and making sure that they get the ability to use the language they want and any particular library that allow for them to be able to use the most recent open source libraries that actually have, and we have the ability to actually do that. And that's one of the reasons why sort of we decided with the premise that we're going to keep it open in the sense that new libraries that come in today can be integrated into the MLflow, and people can start using it and tracking it with the APIs. And so those are the 4 different modules that are discrete, but you can actually use them either collectively or you can actually use them separately. And they provide you the ability to actually do your ML lifecycle from conception all the way to deployment. Now, before I get into tracking, I just want to sort of clear some concept. What do we mean by tracking? And these concepts probably are not new to you if you come from the old data science and machine learning program. You might be tracking these parameters. You might be using hyperparameters. Metrics are things obviously you want to measure. The RMSE, root mean square, accuracy, loss. All those are metrics, that numerical values that you care about, that you actually want to keep track of. Tags and notes are annotations that allow you to document your entire process. So this is actually good for provenance and governance as your model actually evolves, so you can actually track them. And artifacts are things that you're going to create: files, data file models, validation data, and all that. Obviously important is source. What source was actually used, what version of the code was used, and how many runs can you actually run. An experiment is nothing but a collection of actually different runs, because you might just not have one run. You might create a scikit-learn model that's actually doing regression, but you're going to be using it with different hyperparameters, and each run will create its own version of the particular model with different runs on it. And so the entire set of runs will create an experiment, and then you will go through all these different runs to evaluate which was the best one that actually give you the best metric that allows you to go back to the goal of machine learning, which was make sure that the metric is something that you're confident with and you can deploy the model. So what was the world without MLflow tracking? Now, people use tracking in different ways, right? Here's some very simple pseudocode where you can actually use to load a particular model, and you're doing extract n-grams, and you can probably write this to a particular log file, and you can just name the particular log file something else. But what happens if you want to expand your input, if you want to change your input parameters to something other than n equal to 1 or n equal to 2? So you've got to rerun the experiment, you've got to create another log file, and then append those output. What about if your tuning parameters is changing? Let's say your learning rate is different that you actually want to use. So now here you got to create another run and then create another log file, and so on and so forth. And if you take this to the logical conclusion, you can see that it can become quite cumbersome. What if I need to upgrade my library? Now I actually have to rerun the experiments again. And what if my version of the code changes? What do I do then? And it's not that people couldn't do it. It's not that people weren't doing it. People were doing it. They put it in a relational database. They create a particular table, and they can put queries on that. But there's a lot of extra boilerplate code that you actually have to write. And so the idea was that what about if we give developers very simple APIs to take the existing ML applications that actually have, and then infuse that with this MLflow, very simple tracking APIs, very simple. You just import MLflow. The code doesn't change, and the only thing that actually changes is that while you're running the particular experiment, go ahead and log your parameters for me. And so when you log this particular parameter, you can log the data parameter, you can log the file, you can log metric, and you can actually log the particular model that actually saves that particular pickle log file. And then in the UI, you can actually look at all the different parameters that you actually use for different runs. You can actually look at any of the GIF created. You can actually compare different runs that you actually have. You can check the parameter and metric and so on and so forth. And this was our idea of making tracking easy for people to take the existing code they have and then just have to write this MLflow tracking mechanism so to track anything they actually want to track, in particular related to the modal entities. And to make things even life easier, we decided to go one step forward. You said, instead of you sort of having explicitly to, say, go ahead and log this metric and go ahead and log this metric and go ahead and log this parameters, this can actually be quite long, because in certain large models where you're actually going through hyperparameters testing, there are going to be a lot of parameters that you want to keep track of, a lot of metrics that is going to be created. So we have this notion of calling autolog, where you can actually enable in your ML code, just say MLflow library name .autolog, and it figures out what are the things you actually want to log, what are the parameters you want to log, what are the metrics you want to log, and it automatically actually logs that. And we are sort of making constant effort to take all the libraries, all the ML frameworks that we actually support right now in MLflow, and then provide you with this option to say, go ahead and auto-log that. And the current library integrations are the ones that you actually see on the left-hand side that allow you to do that. And when you just do one simple call, you get the benefit of auto-logging all the parameters you actually need. And I think this is actually a great way to make your code a lot simpler, to make it less cluttered and readable. And that way, your existing machine learning code, you don't have to rewrite anything. You don't have to change anything significantly to make it as part of the MLflow. You just have a couple of import statement, context manager with start, run, infuse your code in there to auto-log something, and you're done with it. And so the tracking server is where all the entities are actually stored, right? So you have an MLflow tracking server that actually has the client APIs that talks through the REST API. There's a Java API, R API, and Python that talks to the tracking server to create all these entities for it. The local apps can actually do that. So if you have, IDE environment that you're actually running on, you just import the libraries and do that, or you can actually create that as a cron job and run it. And then on the far right, you actually have the consumers who can talk to the tracking server and extract anything that you want to deploy that. So for example, the MLflow UI is one of the client tracking server that extracts the data and then presents it in a manner. Now we have APIs that allow you to do that the same thing. So if you actually wanted to write your own dashboards that allow you to display the metric, you can actually do that using the APIs. And because the fact that we have integrated as a Spark data source, you can actually use the experiment to extract on Databricks. You can extract an experiment and get all the entities that you want as a data frame, and then use the SQL to create the data frame, if you're familiar with Spark, to do that. And this is very simple. You just set and export URI where your tracking server is running. You set that in your client code, and you're ready to log. Now, there are different configuration, different scenarios where you actually use a tracking server. One is using the tracking server on local storage. So if you're running something locally, you don't need to have a tracking server because you're using the local file system to store your entities where all the ML runs directory is created for you, and all the entities that all the experiment data is actually created under the directory. And if you're using the SQL DB to store your entities, then you just create an SQLite compatible entry for you on the local storage. So there's a local storage people can run on the local machine, or they can run on a cluster if they actually want that. Now on a remote cluster, the entity is the same. You actually have a tracking server running remotely, and you talk directly to HTTP using the and we use a protobuf to send all the messages back and forth. And this is very simple. Again, you just export your tracking URI, you set it in your client, and you do that. Now, if you look at the APIs for the tracking, you have all these different things on the left-hand side. The two most important things that you probably will use in your experiment is the MLflow Fluent API, which is commonly used. It gives you access to almost all the entities that you need to log, all the entities that you need to query. We call it Fluent because it's very Pythonic, follows all the Pythonic protocols. So it's very easy for you to sort of expect when it returns your particular object, you can use iterators on top of it. You can actually use properties to access stuff. It's a very Pythonic way. That's why we call it the Fluent API. Then there is all these other, what we call MLflow modal flavors. And these are the modal flavors for the ML libraries that we actually support. So if you had a model that was using any of these particular libraries, you can actually use MLflow to track its relevant MLflow entities. And when I talk about MLflow entities, I mean parameters, metrics, artifacts, so on and so forth. And then we have the more CRUD API, where you actually want to create a run yourself, you want to manage the run yourself. This is sort of more of a low-level API we call MLflow tracking. And this sort of gives you the ability to track things more in control that you actually MLflow does all this thing automatically for you. MLflow tracking gives you the more control over the low level aspects of it. So you have these set of APIs that allow you to do that. And they're very simple. They're very well documented. And I have been going through all the APIs and putting a lot of sample codes. If you actually go to the MLflow API code, you will actually see a lot of code examples that allow you to do all these things. Now, very simple. On a local host, if you're running, there's no MLflow tracking server running. Everything is stored locally, and it's very simple. I do a MLflow start run with my run name as a default, and then I have my hyperparameters I define, and then I create my random forest of parameters, and I start doing the training, the fit, and all that. And then when I'm done with that, I just log the parameters, or I can just do MLflow log, auto log, and then do my fit training, and it will log all the parameters. And you'll see some of the examples later on. And so what happens when you actually run something on the local, it actually creates a local directory for you. And within the local directory, each experiment is numerical value. So there's a 0, which is by default. And then you have a unique ID, which is the run ID. And then underneath, you have all the artifacts stored for you. Everything you actually need about the model that actually is stored into your parameters. So that's very easy locally. So people who actually want to use on the IDE, or they will use on the local machine, can actually use it quite easily, or they can use it on the Databricks, which you're going to use today. Everything is managed for you. You don't have to worry about it. And if you're running remotely, if you're running locally with the SQL compatible registry, where your entities are not stored in the files, but they're stored in an SQL compatible database. That way you can actually scale your experiments, because if you're running on a local file system, each and every parameter actually has a file descriptor associated with that. So if you have 10,000 parameters, you can imagine what will happen on a local file system. So if you're using the local SQL Lite compatible backend repository, then everything is actually stored locally, and now you can actually scale it on locally as well. And again, this it translates to the same thing. When you run this particular code, you're going to still create the ML directory with all your artifacts in there, but all your MLflow entities are not stored as files, but they're stored as tables in this particular SQL.db repository locally. So this allows you not only to scale locally, but also if you want to do it remotely. And the same thing happens if you actually want to use the tracking server remotely, and where you just launch the server somewhere remotely on your Kubernetes cluster, or wherever you're actually running on the cluster, with the backend stored to be your SQLite compatible, or you can use MySQL, or you can use PostgreSQL, and your default root directory to be where you're going to be storing your artifacts. And then you just use that particular URI to set in your tracking, and then you use the same code, and now it's going to log remotely to the particular server, and it's going to store on a large database with files which are large artifacts that are stored on the S3 bucket, or an NFS mounted file system, and so on and so forth. So at a high level, if you're using the set of APIs for Fluent tracking, they are this Python high-level operations that run the experiments and the model flow APIs. They get converted into its equivalent MLflow cloud operation, right? So these now can get converted into MLflow client, which then actually gets converted into the REST API that actually makes a call to the REST endpoint on the tracking server. So the flow is you create a high-level API, it gets converted to its equivalent low-level CRUD operation, which then has the handler for it to send it to the REST API. So that's sort of so much for tracking. Something we actually recently introduced in MLflow 1.1, which was released a couple of months ago, is that now you can actually also log your signature. So if you're actually training a particular model and you want to make sure that your schemas are compatible, then what you could do is you can infer the schema after you train the model to say, here's my training data set, and here's what my labels, and infer the signature. What is it that I need to be as part of my signature so that when I put something in, I'm going to get the right out. So when you look at the particular schema, it sort of gives you the entire schema, what inputs are for your features and what the output is going to be for the precision. So this sort of somehow allows you to make sure that your schemas are compatible when you deploy a particular model. If a new feature comes in and you try to train the particular model and we try to infer it, you're going to have an error. The other thing that we actually recently introduced is the explainability. Now, you know that when you're building the models and you're doing large-scale prediction, governance and provenance is an important part of it. And explainability in machine learning is an imperative. So you actually want to find out what particular features affected the metric. And so you can actually use SHAP as one of the ways where you can actually take your particular model, create a SHAP feature explanation, and then log that as an entity that you can actually look in the MLflow UI to see what features actually moved the needle, or what features were imperative, or what features influenced the outcome of the particular metric. And I think that's an important query to have, and it can pretty much log that for each and every model that you actually use as a SHAP. The other thing we actually did very recently, which was just a couple of weeks ago, we worked with the PyTorch, Facebook PyTorch engineering group, to integrate PyTorch end to end, where you can actually have the model conception from beginning all the way to deployment. So using PyTorch, you can actually do the auto logging for PyTorch Lightning models. You can actually convert the PyTorch models they actually have and convert that into a Torch script, so you have a more efficient compile model that you actually have, and then you can deploy that particular model using the Torch serve. So if you're building deep learning models in PyTorch Lightning, you can actually convert that then not only to the regular PyTorch model, but also convert that into a Torch script and then deploy that into a Torch server. Now, there's a blog out there that we actually wrote that actually explains all that. And the idea is very simple, right? Just 3 or 4 lines of code after you have done the training, it allows you to capture all the parameters automatically that Lightning is going to do, including your callbacks, your validation step, all the entities that you actually need to autolog. Those will be captured for you after you do the fit training by just one particular call. And this then can take the particular model and then deploy that using MLflow deployment API. If you have a Torch server running, you have to create an instance of Torch server, but that's beyond the scope of this. But what I'm saying is that with these tracking APIs now, you can actually do end-to-end development of the model and deployment using PyTorch and MLflow. And just to give you a quick idea of this entire step of using PyTorch, you can actually train the models. You can register them in the model registry, and we'll get to what the registry is momentarily. You can actually create a Torch script server. You can deploy that using Torch serve. And this is sort of end-to-end way of taking your model and then deploying that using Torch serve. And Torch serve has all this MLOps operators that you can actually monitor the model. And so there's another blog that we actually wrote in joint with PyTorch people that actually shows what the MLflow integration is. So at a high level, we have covered almost 20 minutes. I want to get into some coding as well. So what did I talk about today? I'm talking about the MLflow actually has a modular greatly component. It simplifies ML because it allows you to do tracking and then create a particular model. It's very easy to install, very easy to use. You can use it on one machine or you can use it in the cluster. But the idea is that you can actually do things locally as well. And that's an important part because most developers like you would want to work on your local host. And obviously, it covers all the APIs. You got Python in R, which is almost at parity. Scala client is still we are working on. Java, we actually have a Java client, but Python is a full set of APIs. And it allows you visually to somehow compare all the parameters and metrics that you actually want to compare. And if you want to use it, if you haven't heard it, if you heard it for the first time, pip3 or pip install MLflow. We have loads and loads of documentation. I've put a lot of code examples there as well, a lot of code snippets that show you how to use this particular API. You can join our Slack channel where we field all the questions that people actually have been asking. We have a lot of MLflow tutorials as well. And that sort of brings us to the end of the first module. Let me see if I can go back to my stop sharing and see if there are any questions. Okay, do we actually have any questions? I know I went through a lot of material. The good thing is that these are going to be available for you, so we should be able to do that. Okay, brilliant. I don't see any questions. All right, let's move on then. So the next thing we're going to do is now go to our Databricks Community Edition. Now, I'm assuming that you guys have created, or at least registered, oops. It's a direct message. Hi, Jules. Okay, so the next thing I'm going to do is go to the community edition. So let me see if I can share the screen. Now I'm assuming that you guys have gone through the registration process and you have created a cluster, or at least are logged into the community edition. How many of you actually done that? Can you just give me a quick ping? How many of you actually have created or registered for the community edition? Anybody out there? Okay, I'm just assuming that you have registered for the community edition. So let's go to the community edition. So when you register to the community edition, this is what you're actually going to get as your home screen, right? When you log in, you'll get this particular browser. Let's see if I shared this with you. I didn't share it. Let me share it. Okay, so this is your welcome screen to the Databricks Community Edition. This is a community edition, which means that it doesn't have all the enterprise features, but it has enough features for you to get started, to learn things, great for learning experience, great for workshops, great for you to get started with, whether you're using Spark or whether you're using machine learning. It's a great way to explore what the platform allows you to do. On the left-hand side, you have the ability to look at your workspaces. Workspaces, think of workspaces the way you actually create that, your notebooks, where you can organize them in different projects. So when you click on the workspace, you will actually get your home name. You get your workspace called Jules Damji, which is going to be your login for that. And when you click on that, you will actually get the list of those things. You can actually go down to data and import and create tables and files. We won't get into it for the time being. You can actually create the cluster. Now, what I want you to do today is to create a particular cluster. So create on the cluster, create this particular button. Go ahead and just type in the cluster name that you actually want. So let's do JSDTMLS. And go ahead and create, let's be brave, let's use 7.5 ML beta. Make sure you choose ML or ML machine learning cluster so that you get all the libraries installed for you. You don't have to install yourself. So I'm going to be brave and I'm going to use 7.5. And let's go ahead and create a particular cluster. So this allows me to create the cluster. And then the next thing I'm going to do is I'm going to import my log file. I'm going to import my tracking experiment. Now, the way to import that is that go to this particular workspace, do an import, click on the URL, go to the GitHub. Assuming you guys all have that link, go to the GitHub, click on tracking. go to the notebooks, click on the MLflow DBC. Now you can either download this thing or you can actually just do cut and paste of this. And then go back to your tab and include in there. And when I do an import, this is going to go in and create this particular directory called MLflow tracking. And when I go into tracking, I'll have my notebook. And I click on that, and voila, there is my notebook that we actually going to go through to do the experiment. Okay, the next thing we're going to do is we're going to attach my server to this particular notebook. So this is still spinning. It's actually creating. So I'm just going to go ahead and attach that. And that's going to attach my cluster. So what we actually have over here is that we actually have a small regression model. And I chose a very small model here for the reasons being that this is not a class to teach you how to do data science or regression. But the idea is that how you actually take an existing model that you might have and then infuse that with the MLflow APIs so that you can start tracking experiments. Okay, so we're going to do that. And so what I'm doing is we actually want to predict the gas consumption in millions of gallons in 48 states based on some key features, for example, the petrol tax, the capital income, the number of miles in highway, and the population that actually has licenses. So this seems like a good regression problem to have, but not if you actually are dealing with a lot of consumption problems. So the solution obviously is we're going to create a bunch of runs and we're going to measure all the different metrics that we actually have. And then based on one of the metrics, we'll choose the best source we have. Now, this particular example is borrowed from and modified and modularized for this particular tutorial. And the idea behind here is how can I use MLflow tracking API to track my experiments, to track my parameters, to track my entities, and so on and so forth. Okay, so the first thing we're going to do is we have this particular thing called run setup.class. Now, this is just like if you're using Jupyter Notebook, this is just like a percent or an exclamation command name. Percent run, we call the magic command. The good thing about having the ability to run other notebooks is that if you have some code that you actually want to use over here, if you have some classes that you actually want to use, you can actually run this particular classes on this particular cell, and it's going to bring into scope any classes, any functions, any variables, any data paths that you have that you defined over here that come into the scope. And the reason I do that is not so much that I like to partition things, but I think it's a good engineering practice to sort of delegate those high-level classes into packages, just like in Python we do import thing. This is something very similar to do import thing. And once you actually do an import of something, you have access to those libraries, to those utilities, and so on and so forth. And this is also a good way to modularize your code so that your main notebook that's going to be using this is fairly short, and it's like a main program just calling all the different functions and so on and so forth. Okay, I should have actually created a cluster ahead of time, knowing that all of you are creating cluster at the same time, so it's going to take me a little while. But while we're doing that, let's go ahead and look at what this file looks like. So I have a class setup. If you look at the setup, all it's doing is calling these two other notebooks. So let's look at what those notebooks are. Let's look at lab utils. All I'm doing is I'm just importing some common classes that I'm going to use. I'm going to create a particular class, and then I'm going to create all these my static methods so I can use them. I'm going to read a particular file. I can create a plot, things of that sort. So these are all the entities. These are all utility functions that I'm going to use. So I've created that in the class. The important bit is here, right? This is my main class in which I'm creating a random forest model, and I'm using the scikit-learn, and I'm importing all the appropriate things that I need, but I'm sort of modularizing this so that I can actually use this model again and again. So I have my class called random forest. I have some, class variable called RMS in estimator, so I can keep track of what are the estimators that I actually used. And I have my constructor that allows me to go in and construct this particular class with these hyperparameters as my instance. I have a class method instance that allows me to create a new instance so that I can run different experiments with that. And then some regular properties that I actually have that I can run. Now, here's the bit that is infusing your existing machine learning model that you hear with MLflow. And I'm just call it MLflow. You can call it anything. And I'm not saying that you should use this particular methodology, but this gives you the ability to somehow delegate that to the model itself. And my MLflow run, all it's doing exactly the same thing, right? I'm just starting using the context manager, MLflow.start run. And I'm just going to give some run name so I can identify in my UI what that run name is called. And then all this code is not different from what you would use in your machine learning. The only bit here is this bit over here, right? I am now logging this particular model, right? I'm logging the random forest model, so it actually logs the particular model. I'm computing some regression metrics that I actually want to track, so I log those particular metrics, and I'm just going to, keep a global class instant variable called value, so I can look at the RMSE across all the different estimators, and then append those what are the estimators, so I can create a graph using the number of estimators, parameters, and what my RMSE was. And then if I'm using any plots, I can sort of, go in and use log artifact to create that, and just print those out. So that essentially is a very short, sort of quick example of how to use that. So let's go back over here, regression model, and see if this is done. Okay, brilliant. All right, so let's go ahead and go to my regression model and run this. Now, to run anything in a notebook is no different from Jupyter. You can actually go over here and do a run cell, or you can just do control return. It will execute that, or you can do a shift return. It will execute this particular cell and go to the next one. So if you're used to using like Jupyter notebooks, very similar. If you hit shift return, it's going to go to execute and go to the next goal. And what this is doing is actually just sort of executing this particular class and bringing everything into scope. So that's my. It takes a couple of seconds to spin it up. And this is going to sort of, define all my classes that I have. So now in my next cell, I can just use those as utilities. Okay, so that's going to define this. It prints these all out. These are all the methods available to me. And then now I'm going to go ahead and use those to load something. So we're going to load this particular data and just, print the first header of data frame to see what it looks like. So I have all my features over here. Average time, paid highways, driver population, so on and so forth. And I'm going to print out the descriptive to see what it looks like. So that's what my sort of description is. I can look at the mean. I got 576. So I can somehow have a good idea of what my RMSE should be within particular scope of that particular mean. And here's my main driver. All I'm doing over here is I'm creating hyperparameters starting from 75 as my number of estimators all the way up to 200, and then I'm going to increment the parameter by 25. So this is just one hyperparameter I'm using. You can use any other hyperparameters you actually want to use to tune it and run more experiments to see what's the best RMSE you actually get. So let's go ahead and actually run this. Now you can see that the main code over here is very simple, right? It's just very few lines of code, which is using the driver class to run my experiments. And now I'm going to go ahead and print those variables out. And you can actually see that at the end of 3 run, with my estimated trees starting from 75 with increments of 100 all the way up to 125, you can actually see that my RMSE is actually decreasing. So my model is converging as I actually go down. And you can see that the best estimator is probably around 125, which is the lowest that I actually have. So anywhere around 150. Now you can actually see that over here in this little icon, you have this green light that show you what the experiments are. You can actually click on that. And then this gives you the rundown of all the experiments you actually ran. Right, so this gives you the hyperparameter, the estimators, what were the metrics that you actually load as a summary, and you can arrange them and sort them out So you can you read one at a time, or you can actually use the entire view to look at all the experiments. I'm going to click on this particular right arrow to take me to my MLflow UI. And the MLflow UI is integrated as part of the notebook, so I don't have to launch a separate one. And over here, I have all my matrices, all my experiments that I run. And this is my run name, who the person actually ran, what the source was. If this was under Git version, you could actually have the Git version associated with that. Since this notebook was not part of the Git version, I don't have a Git associated. But normally, if you're running this on a local host, or if your notebook was checked in and you checked out from the Git one from the Databricks, you could actually have the Git version. So you know exactly what version. Here are the models that I created, and this is all my list of all the hyperparameters, right? So I can actually compare to say, let me just compare the first three to see what they look like. So I can compare them by side, and I can see my hyperparameters that actually gives me across all the three experiments that I ran. I can look at my RMSE and use a log scale to see what the difference is between the two. And I can see that this was my third one is the best one that I actually got. I can go back to my experiments. I can use, search, for example, I can say MSC metrics.rmsc root mean square greater than 60. And it will only give me all the root mean square, which are greater than 60. So it's a great way for you to somehow browse through all the experiments that you actually ran in order for you to figure out, what was the best run. Can I tune something? Can I actually improve my RMSE? Can I actually bring it down? So let's go back to our model over here. And we looked at the AI. We saw that with 20 trees, our root mean square was at 64. About 20 trees over here, we got 64. So we know that we can actually do that a lot better by creating more trees. And we saw as we started creating more trees, we actually see that. Now, I haven't done validation. I haven't done cross-validation. This is just a quick way to show how you can actually use tracking. But if I actually use cross-validation and if I use validation data, I probably would get a better estimate of my RMSE. The good thing you can actually do with this particular tracking UI is you can go back here. And you can add notes over here, right? My model for TLS, if I can type, brilliant. And this would be my note. I can actually have, since this is in HTML, I can have PDFs in there. I can have links to the outside. And this gives you a good idea to document your particular model as you start choosing those things. And I can actually save this particular model. And I can go to the model itself and look at all the different entities it actually has. I can have all my metrics. I have my tags over here. And this is where the interesting part comes into bit, is that here's my random artifacts that were created. I created a particular model. It actually shows me what the model is. If I look at my conda file, the conda YAML captured the dependencies that I have. So in order for me to create this particular model, I need all these different dependencies that I need to recreate that. And we talk about projects, which are going to be next. This is where you can actually recreate an instance of a particular project by having these dependencies captured so that I can recreate that. I created my estimated plot. So this is what my plot looks like. I can artifact, I can store that. And here's the other part that we actually introduced in 1.2 is that we actually give you a little code snippet so you can actually test your prediction. So if you want to create this as a Spark UDF, you just cut and paste this particular code and run it, and it will give you the prediction. If you actually use the pandas, just use particular Python to load as a Python function, and then just use the pandas to send the data they actually want, and it will predict that. So this is a good way for you to quickly test this right away from your browser. So that somehow brings an end to our tracking. I have some homework exercises for you, so you can actually go home and work on this. I know we don't have time to go through to do exercises at home, but I think this will actually give you a good hands-on workshop that you can change it, add some parameters, change the depth of the tree, add some more hyperparameters such as random forest, maybe add validation tests to see actually makes a change, makes a difference in the RMSE, and run a couple of experiments to see can you actually see the curve going down, and then finally try the MLflow autolog and see if that actually works, right? Because the autologs gives you the ability to somehow not explicitly log everything, it will automatically log everything for you. And then finally, if you actually have an existing model that you actually have, that you actually train, see if you can actually take the MLflow API and infuse that with that particular model and see if you can actually run it either over here in the Databricks Community Edition, or you can actually run it on your local host. So let me go back here now to make sure that, now this is actually a great cure for a good antidote for your insomnia. If you are suffering from it, having anxiety, sleeping at night, this homework will definitely cast you into a good comatose. So let me go back here and make sure that I stop sharing and see if you have any questions. If you have any questions, just don't send it to me directly. Just put it here on the chat so I can address them. Okay, so let's move on to the next one then. Brilliant, I like this. People are just zooming by. Okay.
Hey, Jules, there was a question in the chat.
Okay.
Yeah, this one.
Where is that? I don't see it. Can you read that question to me?
Yes, I can. Yeah. So it's a question from Manoj. MLflow seems to have good integration for training pipelines. Is there any support to collect logs and metrics during inferences?
Okay, good question. I think the question is that MLflow actually has a good tracking API, which is true. You can actually track pretty much everything, right? And so when you're doing inferencing, when you're doing prediction, for example, and you get, let's say you get a pandas data frame back, or you get an NumPy array back. Can you log that? Yeah, obviously you can actually log that. You can log that as a file and write this to a file as a CSV file or whatever NumPy array is for tracking, and then or you can actually just log it to a particular path and then use that, add that as a parameter to the run. So you say for this particular model, when I ran, here are my parameters, and here's my tag, and here's my prediction that it came out. So yes, you can actually log parameters. You can log any monitoring data that you actually want when you're doing the prediction. And this is actually a good way to monitor your concept drift and change, because over time the data is going to change. Over time the model is going to decay, and so you want to keep track of those things. And I think one of the things, Manoj, you can actually do is that when you're doing the predictions, one extra step would be to go ahead and log those predictions, and then so we can actually you can do the Y and the Y hat by side, and that way you can plot those graphs later on to do some analysis to see if there is a decay in your predictions, or what you predicted is going farther and farther away from the target. So that's actually a good way to do that. Any other question? Lovely. Let's move on to the next bit. Okay, I got to remember application window.
Sorry, it looks like there's another question.
Okay, yeah, go ahead.
This is a question from Mikaya. It says, is there any way to integrate the log/graph